4.4, evaluating logarithms and change of base theorem. So today we're going to actually deal with evaluating logarithms as opposed to just converting them from logarithms to exponential equations or exponential equations to logarithms. To start with that, I want to refer to what we call the common log. The common log is log base 10. I'm going to put up A. But log base 10 is referred to as the common log. And it can be written as log without a subscript. So when you see log without a subscript, it's referring to the common log, which is log base 10 of that thing. And that's very common, and you have a log base 10 key on your calculator, log of x. It either says log x or log with a little square on it, whatever the case may be. And all scientific calculators have this common log button on it. So you can just plug in any real number for A, any positive real number for A, and get the common log of it. So I'm actually going to grab my calculator here. And do some common logs. So what if I have log of 4? So log of 4, so I'm just going to plug that into my calculator. And I get 0.60205999138, but we'll say that that's approximately equal to 0.602. Well, what about log of 10,000? Or the common log of 10,000. Now this one actually, we probably don't even need to plug into the calculator, because if this is log base 10, then 10 to the what gives us 10,000, and without even plugging into your calculator, you can say that's going to be 4. But just to make sure, we'll plug it in there. And amazing enough, 4, right? And then what about log, or the common log of 1.27? So common log 1.27, so I'm just going to plug that in, and we get about 0.104. Rounded, of course. So those are our common logs. Remember, your calculator has a button on it that will allow you to do it. So it's good to practice that and just be able to plug that in and get an answer. Realize that most of the time you're going to end up with some decimal that's going to continue on, so round it to the nearest whatever is required. I like to see 2 or 3 decimal places. Generally, I like to see 2 decimal places. In this, I happen to choose to do 3 because 0.60, 0.10, I kind of like to throw another one on there then. So those are our common logs. Well, how can we use common log? Well, let's get to an example of how common log is used. So let's get an application. So this is a chemistry application. And in chemistry, pH, how acidic or how basic a substance is equal to negative log of H3O+. H3O+ is the hydronium ion concentration. In moles per liter. So pH is found by taking the negative of the log of the H30 plus, HBO I should say, that's not a 0, that's an O for oxygen, hydronium ion concentration moles per liter. Okay? Now, just a little bit of background chemistry and pHs. A pH of 7 is considered to be neutral. You drink a glass of water, the pH is going to be right around 7. A pH less than 7 is acidic, and a pH greater than 7 is considered to be alkaline. Or sometimes we refer to that as being basic. You have an acid, a base, and neutral. Now, how far away you are from this neutral pH of 7 determines how basic or how acidic that substance is. The more acidic or more basic, the more dangerous for you. So pHs go from 0 to 14. So a pH of 0 would be extremely acidic. A pH of 14 would be extremely alkaline, both of those being very dangerous. You would not want to just submerge your hand in those. Whereas a pH of 7, neutral. So if we're somewhere around 7, that's going to work well for us. We're a little higher, a little lower, not too much of a problem, but you get too far away and that's where you start running into problems. So having that information, grabbing my eraser that fell to the floor, I've determined I need a larger tray for my markers and erasers. So let's put this over here again. So pH is equal to negative log of the concentration of hydronium ions. So we have that there. So we want to find the pH of a solution with a hydronium ion concentration of 6.8 times 10 to the negative 8. So find the pH if the hydronium ion concentration is equal to 6.8 times 10 to the negative 8 moles per liter. Okay, so how are we going to do that? Well, we know the hydronium ion concentration, so we're going to say the pH is equal to the negative log of 6.8 times 10 to the negative 8. And you may want to put that in parentheses just so that you don't just take the log of one part and ignore the other part. And so we can plug that into our calculator, and actually we can do two things here. We can either plug this directly into our calculator as such, which means you better know how to use your calculator with scientific notation, or we do have a product inside the log, so we can take this and make it pH is equal to negative log of 6.8. I'm going to put the negative outside, plus the log of 10 to the negative 8. Now, why is that handy? Well, two reasons. One, it may be easier for us to plug in. Two, we have log base 10 of 10 to the something, which, remember, that means that those cancel out and you're just left with whatever's there. So that just saved me a calculation. So pH is equal to negative log of 6.8. I'm just going to plug that into my calculator because I don't know that off the top of my head. If you do, more power to you. 6.8 gives me 0.8325 plus, remember we said that becomes negative 8. So is equal to the negation of if you have negative 8 plus this, then we have negative 7.1675. So therefore the pH is equal to negative of negative, positive 7.1675. So there we go. So we're able to find the pH. So is it acidic or is it alkaline? It's slightly higher than 7, so it is slightly alkaline. Again, something like that, you're never going to notice the alkalinity, meaning it's not going to affect you if you touch it. You could shower in this and it wouldn't give you any problems. But depending on what you're working with and why you have it, it could. Such as if you are dealing with watering plants, plants may be okay with having the higher pH a little bit above, meaning it won't kill them, but they're not going to be overly happy with it. In fact, most plants are going to be looking for a lower pH than that. They prefer to have a pH closer to 6. They want it slightly a little bit acidic. So having it above 7 is actually a bad thing for them, at least in being able to absorb nutrients. Okay, so there we go. Well, let's work it the other way. Let's do an example where we know what the pH is, and we want to find out the concentration of hydronium ions. Well, we can stick with this same formula, but let's say we want to know the hydronium ion concentration if we have a pH of 4.3. So now we're a bit acidic. So we're going to plug that in for pH, so 4.3 is equal to negative log of the concentration of hydronium ions. Obviously we can negate both sides, so negative 4.3 is equal to natural log, the common log of H30 plus. Now what do we want to do? Well, log, that's log base 10. So if I take both sides and make it 10 to the whatever, that'll cancel out my log, so I can say 10 to the negative 4.3 is equal to the concentration of hydronium ions. Unfortunately, we can't just leave it like that, 10 to the negative 4.3, because that's not scientific notation. Scientific notation has a whole number there. So we're going to have to plug that into our calculator. And if we do so, we find out this hydronium ion concentration is equal to 5.0 times 10 to the negative 5. So that's just plugging 10 to the negative 4.3 into your calculator. And just to show you that it works, I'll plug it in there. 4.3 negative. Where's my key? There we go. And I get 5.01187233627 times 10 to the negative 5. So I rounded it to 5.0 times 10. Don't leave out the 1. 10 to the negative 5. So we can work either way, and that's taking advantage of what we know about the inverses, right? We know that 10 to the something is the same as the inverse of log base 10. So really good to use. Okay, let's go into another example. Chances are you're going to see this chemistry here somewhere along the way. A number of you are going to be taking a chemistry class, and you need to know this chemistry. Others of you maybe not, but maybe you'll deal with physics. And if you deal with physics, you may see something like this. When you're talking about loudness of a sound, we deal with intensity. So the sound intensity level. And I sub 0 is the intensity of a very faint threshold sound. When I say faint, I mean basically that's what you can discern that there's actually a sound. So you're creating a threshold level. So this is the threshold intensity. If it gets to be any stronger, then you definitely hear it. If it's any softer, you don't. And for different people, they have different intensity thresholds, right? I may not be able to hear something, but you may be able to hear it. Therefore, you have a lower intensity threshold than I do for the intensity of the sound. Okay? Decibels dB, and sometimes just done with a D, but decibels dB refers to the sound level in relation to this threshold intensity. And that can be found by taking 10 times the log of I, the intensity of a given sound, over I sub 0, the threshold intensity. So it's basically, we're taking 10 times the log of the ratio of the sound to the threshold. Almost saying how many times greater is it than the threshold. Because if we have intensity, our threshold intensity, and the sound level is that intensity, then you'd have a ratio of 1 to 1. If it's twice that intensity, then we have a ratio of 2 to 1, right? So just looking at that. So let's find the decibel rating of a sound with an intensity of 10 million times the threshold intensity. So 10 million times the intensity threshold. So we're going to take dB is equal to 10 times the log of 10 million times the intensity threshold over the intensity threshold. Now at this point, we may have looked and said, well, we've got a log of a quotient, so can't we just break that up into 10 times the log, 10 times the log of 10 million IO minus the log of IO? We could, but we probably also noticed, why don't we just cancel those? Right? Our intensity level was written in terms of the threshold intensity, so it just cancels out. So we're left with 10 times the log of 10 million. Well, we should be able to answer that pretty easily because, again, log base 10, 10 to the what will give us 10 million. There are 7 zeros, so that's equal to 10 times 7. Because 10 to the 7th will give us 10 million. So our decibel rating is 70 dB. So there we go. So another example of how logs are used. So if you've ever wondered how they come up with this is 54 dB and that's 27 dB, or you don't really see 27 dB much because intensity thresholds really, or the comparisons that they tend to use on a lot of things, are higher. Because just the noise around you, many times when you're dealing with decibels and sound intensity, it really it's not just the threshold intensity that we deal with, but it's the ambient intensity. So basically, right now, if I were to stand perfectly still, I hear the computer running, I hear some noise coming from a clock, I hear some sort of noise, might be the AC system running, but there's these noises that are already there. So when I'm comparing to try to hear something and to determine the level, many times I'll relate that level to the noise threshold. When can I discern that there's something else if I already have something? If I have something that's already making a noise at 50 dB, chances are I'm not going to hear something else that's making a noise at 45 dB because the 50 dB one's louder and it's overpowering that 45 dB noise source. So decibels are fun to look at, and I can tell you I've had to deal with this in real life. They were looking, a number of years ago, they were looking at putting wind turbines into numerous places in the area. And one of the concerns was noise levels. Ambient noise levels versus what the noise level is going to be if you had these wind turbines in place. And so we did many things to verify what would be the noise level, how it would affect people to have them nearby. Okay, so let's transition off of that to natural log. Natural log or natural logarithm is log base e. Log base e. So if your base is e, the Euler constant, which we talked about, right? Then that is considered to be the natural log, and that's written ln of a, the natural log, or logarithm natural of a. And again, your calculator has a natural log key. And whereas your log key tends to be the same key as your 10 to the x key, one being the actual button and one being the shift function of it, natural log and e to the x tend to share buttons. And that's not always true. Sometimes they put both of them on separate ones because they're things that are used regularly. Sometimes they put them together. But the relationship is still the same, that natural log and e to the x are inverses of one another. So we have a natural log. So we can use a calculator to find these. So let's find the natural log of e to the 4. Now, before we even go anywhere, remember, if we have log base something of that same something to a power, the base and that something cancel out. So we have log base e of e to the 4th cancels out, and it just becomes 4. If we did that if we had log base 10 of e to the 4th, then that would not cancel out. But we have log base e of e to the 4th. Cancels out, gives us 4. Natural log of 341. So if we plug that in here, 341, natural log, 5.83188247728. So approximately 5.83. Make it look like a 5, there we go. 5.83. And what about natural log of 0.06894? Again, we can do this with any positive number, so 0.06894, the natural log of that is negative 2.674518711789. So we'll say negative 2.67 will be sufficient. So there we go. So natural logs. And natural logs get used in numerous places, and actually if you go further on in math, you'll see natural logs tend to get used more than common logs. You'll see that happen a lot. So just fun to play with that. Just got rid of my paper there. So the last thing I want to talk about is change of base theorem. So we just talked about the fact that your calculator has the common log, I just couldn't put it of x, and it has the natural log, right? That those functions are there on any scientific calculator, which is really handy. So that works well for you. Some calculators have the additional capability to write the wrong things on the board. No, that's just the professor who has that capability. So log base a of x. So some calculators, such as many of the Casio graphing calculators, the TI graphing calculators, have the capability to deal with a base other than 10 or e. But then again, many scientific calculators do not. Graphing calculators tend to have that capability. But what do you have to do to get there? You have to go, if you have a TI, to get there you have to go into the math menu and scroll through the math menu to get to where it gives you log base a of x. And depending on your graphing calculator, you may not have. My daughter ran into a problem that she was using graphing calculators at school, and they were dealing with logarithms, and she was supposed to find the logarithm of something to some random base, and at school they just plugged it into their calculator. She got home, where we had a TI-84 waiting for her to use, and she goes to it and she couldn't find the function. We later found out the reason she couldn't find the function was because it was in a later software rev, and so we have since updated the revision of her software on the TI-84, and now it has that capability. But it did not at the time, and she needed to do homework dealing with a different base. So I introduced her to the change of base theorem, which says log base a of x is equal to log base n of x over log base n of a. Meaning that if you have log some random base, I just want to make that sure that that's clear, that that's an a. So if you have log some base of something, and that base is not something that you can easily get, it's not base 10, it's not base e, so it's not a common log or a natural log, and you want to find out the log of it, then the change of base theorem says you can take that, you can take the a and the x, the base and the whatever we're taking the log of, and put them here. You choose any base. So you could choose to do this as log base 7 in both of these, but as long as you do that, you take log base 7 of x and divide it by log base 7 of a, and you will get log base a of x. Now, of course, you're generally not going to use 7 if you don't have the ability to plug it in here and you need to change the base, but this means that now you can use your calculator using common log or the natural log to find the log of anything. So let's try it out. Let's go log base 6 of 1.2. So we're going to take log base, well, let's do common log. So I'm just going to do log of 1.2 over log of 6. I can plug that into my calculator. So log of 1.2 is 7.918 times 10 to the negative 2. Log of 6 is 0.778 Now I did the dot and dots and everything because I'm going to just use the values that I have in my calculator. So I have 7.91812460476 times 10 to the negative 2. And I have 0.7781512500384. And I'm just going to divide them. And I find that log to be log base 6 of 1.2 to be 0.102 approximately. It's 0.1017555982996. That's what I came out with, so I'm going to say approximately 0.102. by using the change of base formula. I'm going to do this again using the change of base formula, just to show you that it does not matter what base you choose as long as you use the same base for the top and the bottom. So I'm going to go log base 6 of 1.2 is equal to natural log of 1.2 over natural log of 6. So the natural log of 1.2 is about 0.1823 dot 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 dot, and the natural log of 6 is about 1.7917 dot dot dot. And if I divide them, amazingly enough, I get log base 6 of 1.2 is equal to 0.1017, so 0.102 approximately. And I come out with exactly the same number on my calculator either way that I do it. So like I said, I introduced my daughter to change her base, and she was able to do all the calculations that she needed to just with doing 2 quick logarithm calculations on her calculator. She just used probably the common log. I didn't watch her do it, so I don't know whether she used common log or natural log. Probably common log is what people like to use. And she just quickly did 2 calculations, divided, and had her answer. Did not take her much longer than plugging in here. In fact, it may have actually been a little bit faster because she didn't have to go searching through the directory of functions to find the base function, bring it up, then insert the values into it. So pretty cool. So that's the change of base theorem. So you do not need a special calculator or tool to be able to calculate logarithms for any random base. All you need is the change of base theorem. So that finishes up 4.4, evaluating logarithms and change of base theorem.